Good morning or good afternoon, everybody. Thank you for that introduction and welcome to my presentation on the optimization of green hydrogen production with operational digital twins. Today, I'd like to talk a little bit about some of the opportunities and the challenges that green hydrogen presents project developers and project operators, and also talk about how we can solve some of those challenges with digital twins deployed in an online environment. Let's start with a look at why green hydrogen is so important as we tackle the net zero challenge. One of the most important reasons is that green hydrogen can serve as a vector for renewable energy, storing, moving around, and utilizing renewable sources of electricity in a much more varied range of ways, whether that's for decarbonizing hard-to-abate sectors like steelmaking or feedstock chemical production, or it's providing some of our final energy demand. There's huge forecasted potential, and as a result, demand for green hydrogen is expected to grow really considerably, not only over the next 25 years, but also over the next 5 years to 2030. Let's look at those numbers in a little bit more detail. This first graph presents hydrogen demand by sectors in 2030 under an optimal net zero scenario. We can see 155 megatons per year demand split across use cases like refining, ammonia production, fuel cell vehicles, and many others. If we translate that consumption to a production, we can see the same need split across grey hydrogen produced from natural gas, blue hydrogen, also from natural gas but with carbon capture, and green hydrogen produced from renewable electricity and the electrolysis of water. As we move across this second graph, we can see there's a large amount of existing grey hydrogen, but actually a substantial supply gap, 50 megatons a year, unplanned production capacity, mainly from green hydrogen. So the question for the industry at the moment is, can companies fulfill the market need, close that supply gap, but do so in a way that is efficient and economically viable? Now, to do that, they face big challenges, one of which is integrating green hydrogen technology into a very wide range of uses. Here at Siemens, we're talking to companies that are looking at very large industrial capacity of the order of a few hundred megawatts, but also very small capacity for municipal use. The breadth of interest and the breadth of applications is huge, and as a result, there's a large amount of decentralization in green hydrogen. Lots of stakeholders involved, lots of project dynamics to consider. When we look at the operation of green hydrogen facilities, we can see a huge amount of complexity and uncertainty, whether that's from the natural intermittency of renewable energy supplies or uncertain demand profiles. This is a problem that we'll look into today and is really causing challenges to operators around the world. And finally, on top of all of this, is a very low level of operator experience in the industry, a skills shortage, particularly impacting hydrogen production. The end result of all of these challenges is that the cost of production is too high. That makes it more difficult to justify projects, more difficult to secure investment, and more difficult to run plants sustainably into the long term. So let's look at a mission statement of sorts. How do we address these challenges? Well, we think that to be competitive, green hydrogen projects must first be developed in an efficient way, but then also operated efficiently. And the owners of these projects need to empower their operators with tools and capabilities that can help them increase the efficiency, increase the safety, and increase the reliability of their assets, not just in one day, but every day that plant is running. Now, we respond to this mission statement with the digital twin. This is a well-known concept that simply represents a replica of a project or a process or piece of equipment in the virtual world. They have a lot of capabilities and can add a lot of value to projects either in the design phase or in the operations phase. But to be able to do that, they have to be an accurate description of a real-world asset or process. They have to be predictive over the agreed design space. And in most cases, they have to integrate different capabilities, different data sources to provide benefit to different members of the project team, indeed at different times of the project lifecycle. And if we look at a very simplified project lifecycle for a hydrogen plant, we see that a digital twin is not developed in one space. It's actually developed throughout the project lifecycle, whether that's in concept development, detailed engineering, commissioning, or steady state operation. Now, not only is a digital twin developed over time, it's actually adding benefit over time, bringing value to the users over time. An integrated digital twin should be a core component of a project that affects every stakeholder with a range of capabilities throughout the life cycle. Now, this can mean a great many things and have a great many components, but for today's context, we're focused in three key areas. The plant twin, which is a virtual replica of the engineering information and data in a process. The process twin, which is a replica of the material and the energy flows in that chemical process. And an automation twin, which is, as you'd expect, a replica of the control and automation systems used on that plant. Today, we'll deep dive on how to use the process twin, specifically in operations, that corner of the digital twin world, combining process knowledge with operational need. But to be able to leverage a process twin in the operations phase, first we need to build the process twin. How do we do that? We do that with an advanced process modeling software, in this case, Siemens gPROMS, which is a platform for building physics-based high-fidelity models. A process twin can be physics-based, it can be data-based. Most often it's a combination of the two. And in this software, you can combine off-the-shelf library models of chemical processes with data from the real world and produce a predictive simulation of a single unit operation or an entire system. You can then use that simulation for design optimization, scenario analysis, and risk reduction. But this is an offline environment used to support design processes. The transition to an online operational digital twin has historically been quite complex, but we've developed a platform and a family of products that make this as easy and as efficient as possible, that allows you to do two things. The first thing is take an offline model and put it in an online environment, such that it can be deployed on an easy-to-use dashboard, such that it can support the real-time operation of a facility. And the second thing is that it can communicate with the plant's data sources. It can take information from the DCS or the data historian, but it can also pass information back. Now, this allows it to communicate with the true plant state continuously. It's never a static picture, and that's really important, especially when looking at dynamic operations like in green hydrogen. We're going to look at how we can use such an operational digital twin in a moment. But first, a question. What hinders the deployment of process twins in operational plants? Is it that integration is very difficult? Is it that deployment is an expensive process? Is it simply that operators don't have the expertise needed? It could be any of those. It's actually a bit of a trick question because the answer is all of the above. All of these and more factors besides make it a difficult process to deploy these twins, digital twins, online. The impact of that is that there's a case of trapped value. A process twin may well be developed in the design phase to support design and optimize process design, but if it cannot then be used every day that the plant is operating, we're losing a huge amount of potential benefits. So the question naturally is, well, how do we unlock that value? But first, I'd argue we need to answer, why do we unlock that value? Why should we? And to answer that question, we go back to the same 4 challenges from the start. And the reason why is that an operational digital twin has specific solutions to these specific challenges. It can provide capabilities, integrate data in such a way that we can directly address limits of technology scalability, the fact that there's various stakeholders, the fact that there's limited operational expertise, and the fact that these plants are often very complex to operate. Some of these capabilities: live performance monitoring, aggregating and processing data from different sources, whether it's on the plant or from an external source, and showing those to operators, providing that real-time insight. Analysis of individual equipment, understanding how equipment behaves, how its performance compares to where you'd expect it to be. And that helps you plan production more effectively. It helps you take a proactive approach to maintenance, not a reactive one. And finally, production and process optimization, tackling uncertainty, tackling complexity with mathematical optimization. We're no longer using optimization just for design, we're using it to support a running plant in near real time. Let's just zoom into that third capability for a second. What's a challenge that operators face? Well, put simply, they need to meet objectives as efficiently as possible. Now, in the context of green hydrogen production, what tools do they have available? What decisions do they have to make? One of the most simple ones is, how do I operate my electrolyzer stacks? How should I ramp them? What loads should I distribute across the cluster? Which ones should I turn on or off? But the decision complexity really increases beyond that when we look at things like storage management. When should we store hydrogen? When should we discharge from storage? When should we store downstream products? More fundamentally, the question is, well, when should I even produce hydrogen in the first place? And what power supply should I use to produce it? Should I produce on grid power or renewables? When should I produce during the day? How can I ensure that I'm always going to meet my off-taker agreements? And this complexity only increases when looking at downstream projects like Power-to-X for green ammonia, for green methanol, for sustainable aviation fuel. The complexity really spirals. Now, the result of all of this is that, firstly, decisions are very difficult to make, but they also have to be made under significant uncertainty. Sadly, we can't just make these decisions once. We have to continuously make them and remake them, re-optimize. Why? Because we operate in an uncertain space. The weather forecast might change, impacting your renewable energy supply. You might lose the demand off-taker very quickly due to a malfunction downstream. So you can never rely on one optimization. It's always an iterative process. And the reality is, in order to reach and maintain optimality, operators can't do it alone. They need digital tools, online applications running in real time to answer these very questions in a rigorous way. And that's where our digital twins step in. So that's an introduction to why we should unlock this value. Now let's go back to how we can do so. And our response to this challenge, specifically for the green hydrogen Power-to-X industries, is what we call the Hydrogen Performance Suite. This is an online standardized application that takes a high fidelity process twin and places it in an online environment connected to a real running plant. Now, this achieves 3 key capabilities, the 3 that we talked about a few moments ago: performance monitoring of the assets, easy visualization of KPIs, easy processing of data, making sure that operators are always informed about the status of the plant and any concerns or challenges that are arising. The second one being real-time optimization, understanding when to produce, how to produce, maybe even what to produce if you're on a downstream Power-to-X or industrial cluster. and then equipment soft sensing. Soft sensing is very important for understanding the behavior of units, especially electrolyzers, determining how their performance is changing over time and whether you should adjust production plans, schedule maintenance, etc., to respond to what is being observed. Now, all of this is only possible with tight integration with a plant's automation system. Data from sensors, from the DCS, from the data historian, continuously flow into an application like this to make sure it's always got the most up-to-date information and can make the best decisions. Now we'll come back to the screenshots in a couple of demonstration videos shortly, but first I want to show where this application sits. If we consider here the traditional OT layer in a plant, we have the physical process at the base and then different levels of automation, ultimately peaking at the top with the automation HMI. Now the hydrogen performance suite sits directly on top of the OT layer, in the IT layer. And it sits on top and then receives information from a lot of different sources. We receive information from the plant itself. We receive information from off-takers for demand profiles, for price information. Of course, the users specify targets and optimization objectives. We receive information from the power grid, from renewables. We also critically receive information from energy management systems. There's a close communication between the hydrogen performance suite and power optimization, power management. Now within this application, there's still that underlying core of the process twin that's been deployed online, ready to achieve those three use cases: real-time optimization, performance monitoring, and soft sensing. But all of this is made easy to access with a simple user interface that non-expert modelers can interact with, can receive advice from, can make changes to. So let's look at a couple of videos. The first one will demonstrate real-time optimization. There's no audio in this video, so I'll continue to talk over it. So in this case, we see that homepage you saw in the screenshots. This provides real-time information for all of the KPIs that are needed, whether that's production, storage capacity, energy use. And here we see a much more detailed view of the process. We'll come back to that tab in the next video. And here we have the energy management dashboard. This allows us to create hour-by-hour production plans, deciding when to produce hydrogen, how to produce it, considering data from the plant, data from the renewable energy sources, data from the demand profiles. All of this is integrated into a mathematical optimization. As we see here, the hydrogen demand in this scenario is dropping, and an optimization is completed. I'll just pause the video to be able to decide how to respond to that change in demand in the most efficient way. In this case, the objective is to minimize the use of grid power. So how do we produce with that objective in mind, while still meeting all of our demand requirements and our operational constraints? And this is a problem that can be solved not only every day, but also within a day, within an individual production period, if we see something unexpected happening. Maybe the weather changes suddenly and we need to adjust our operational plan. The model and the application allows you to do that live. So now let's look at a second video for soft sensing. Now we'll dive into a little bit about equipment monitoring, performance monitoring. The same overview page gives us KPIs for energy usage, production, electrolyzer performance, and the schedule optimization. Now, if we go to that process flow tab with the detailed view of the system, we can see some variables that are being measured with sensors. We can also see some variables, in this case with the pink background, that are being soft sensed. That means they're being calculated using a combination of that process twin, that process model, and other data provided across the system. If we dive into the electrolyzers and have a detailed look, we can now see the performance of that electrolyzer. In some cases, these values are being measured once again, but also values are being soft sensed. We can calculate an efficiency and compare that to our expected efficiency, in this case, the baseline. We can look at how degradation changes if we have a suitable model. All of this allows us to make better decisions about our equipment's performance because we're no longer relying on a static picture. We have a real-time picture of the equipment state, which is a much better foundation for decision making. So just to finish with a case study, this is a company here in the UK called Protium Green Solutions that have followed this two-phase process. First, developing an offline process twin that they've used for design support, design optimization. And secondly, deploying that process twin in an online environment. In this case, you can see the dashboard that's used for production scheduling, monitoring of different electrolyzers within their cluster. The dashboard is slightly different to what you've seen in the videos. That shows the flexibility of this platform to meet specific needs for specific projects. Also shows the speed of development of these applications. So some of the benefits we'd expect to see from a system like the Hydrogen Performance Suite: directly addressing that core challenge, reducing cost of production, improving energy efficiency, improving maintenance planning. It's also about de-risking assets, providing all of the information needed to run not only efficiently, but safely and reliably. And then being able to scale deployments, whether that's across multiple assets in a fleet or an industrial cluster, or adding new functionality, new data sources over time. But this area of development is fast moving and lots of features, functionality is continuing to be developed, whether that's extending these applications to new downstream uses, hydrogen liquefaction, sustainable aviation fuel, e-methanol, etc. And critically, one area of interest is integration between the energy management systems and the Hydrogen Performance Suite, combining power and process optimization to happen simultaneously in a single application. We think that's going to realize what's termed here as the holistic digital twin for hydrogen assets, where it's going to deliver even more benefits to a combined monitoring and optimization tool than could ever be achieved by two separate tools. And that's something we're developing actively at the moment. But with that, I'd like to conclude. Thank you very much for listening. I'd be very happy to answer any questions today or to hear from you after the event. So thank you very much.